Hello everybody. In this video, I'm going to build up the essential components of a simple interstitial diffusion random walk model in NetLogo. And I'm going to assume that you've already seen the intro to NetLogo video or have some experience with NetLogo. So I'm just going to jump right in and create a setup button, even though I have not yet defined a setup procedure, and it turns red because nothing named setup has been defined. So I'll go to my code tab and I'll define my setup procedures. So like normal, I'm going to clear all. And then for now, let's just create turtles 1 and reset ticks. I always like to just check that things are working in small intervals. And since we're going to be, this time we're really thinking about atoms. So I'm going to go ahead and set the default shape of turtles to circle. And that way I don't have to do it manually each time. That looks good. And that's it for now. I'm going to go ahead and go to my Go procedure. I'll go back and modify the setup quite a bit, but I'm going to go ahead and go to write a Go procedure. And I'm going to do something that might seem a little funny, which is I'm going to ask my turtles to do something that is undefined right now. I'm going to ask them to random walk, even though that is undefined. So if I try to go to my interface tab, it's going to give me an error that nothing named random walk has been defined. Then if I really want to go, I can click interface again, but the code tab will be red because I have this error. So now I'm going to define my random walk. And there's a lot of ways to do this. We're going to be, for this model, having the diffusing turtles or atoms just move to one of their 4 nearest neighbors. We're gonna imagine that the patches are interstitial sites. And so if I ask this patch to just return its neighbors 4, that's a built-in command, it's going to give down here an agent set of 4 patches. It doesn't say which ones. But if I ask those neighbors 4 to set their p color to red, let's say, now you can see that this patch 30, its 4 neighbors are patch 31, patch 40, etc., the 4 surrounding neighbors. If you just do neighbors by itself, then you get the corner neighbors as well. We're going to use neighbors 4. And so there's also a command move to for turtles, which is to move to a patch. And so these turtles are just going to move to one of neighbors 4. Neighbors 4 returns an agent set of the 4 neighbors of where this turtle is. And turtles don't have 4 neighbors because they can move around. So when a turtle uses neighbors 4, it's actually asking for the 4 neighbors of the patch that it's currently located on. And then it's just going to select one of those 4 neighbors randomly and move to it. So let's see if that works. Let's go ahead and create a Go button. And we'll make it a forever button, and we'll disable until ticks start. So let's set up. We've got our atom there. And if we click Go, sure enough, it's wandering around quite quickly. And if we ask this turtle to pen down, now the pen mode is down, we can see that it is indeed tracing out a path that is consistent with a square lattice. And since it's only one turtle, if we let this go really long, it'll actually end up going everywhere in the world and tracing out a full square lattice. Okay, so we've got a basic random walk already with one turtle, but we'd really like to make this have more turtles so we can model a more realistic system. So the first thing I'm going to do is something you haven't seen yet. I'm going to define a new breed of turtles, and that's because I'm going to end up with 2 different types of turtles, and this makes it easy to keep track of them. So the way you define a breed is you type the word breed, open brackets, and then you have to put the name of the breed in plural. So I'm going to use D atoms for diffusing atoms, and then the name in singular, so D atom. If I was making a breed that was going to represent, let's say, horses, then the first word would be horses, and then the second one would be horse. Okay, so instead of turtles, now I'm going to create D atoms. And instead of asking all turtles to random walk, I'm going to ask datoms to random walk. And when we create the datoms, let's change how they look a little bit. I'm going to have them all have the same color, set color to yellow, and let's also make them a bit smaller. Okay, so that looks fine. And now I would also like to, just for visualization, let's create a different type of turtles that are going to be our lattice atoms. And so just so that it's clear that this model is interstitial diffusion. So let's make a new breed, L atoms for lattice atoms. And now I'm going to ask patches, because I want one of these for every patch, but then I want them in the corner of the patches, not in the center. So at the center of the patches will be our interstitial sites for the diffusing atoms to diffuse on. So I'm going to ask patches to sprout L atoms, one each. This is a built-in command where a patch will create a turtle, and the turtle will start out sitting on top of that patch. And let's make our L atoms blue, and we'll set the size to slightly smaller than a patch size. By the way, these sizes are relative to the size of a patch, so size 1 would be the same size as one patch. And if we do that right now, we get these L atoms, but they're in the center of patches right now. If I inspect this patch and I set the P color to red, you can see that this is in the center. So I need them to move to the corner. So we'll have all of these L atoms set their heading to 45 degrees. So they're facing the upper right corner of the patch they started in, and then they need to move forward. This is a hypotenuse of an equilateral triangle, so square root of 2, but it's only half of that because they're starting in the middle of the patch already. So divided by 2. And, whoops, set heading. Okay, and now we can see, if I inspect this patch, set the color to red, that's the patch, and we see that there are these lattice atoms on each of the corners, and we've got our one diffusing atom right now in an interstitial site. And again, these blue atoms, these lattice atoms, right now they're just for visualization. They're not actually adding any logic to the diffusion right now. Later on, you could add something where they actually affect the diffusion. Okay, and the last thing I'm going to do is we want to have more than just one diffusing atom. So we'd like to have an initial concentration. So I'm going to create a slider. I'm going to call it concentration. And it's going to go from 0, increment by 0.01 to 1. So if we have a concentration of 1, then every interstitial site will be filled. If it's 0, none of them will be. Let's start it at, I don't know, 0.3. And now we need to use this concentration to somehow decide how many diffusing atoms to make. So down here, we're again, instead of creating diffusion atoms, I'm going to do the same thing I did for the lattice atoms. And I'm going to ask the patches to sprout D atoms. Instead of create D atoms, sprout D atoms 1. So right now, this would just create a diffusing atom on every single patch. We can check that that's true. Yep, so we get, right now we get a diffusing atom on every patch. And if we click go, they will diffuse around because there's nothing in the logic right now that says they can't move to a neighbor that already has a diffusing atom there. So they'll diffuse around. But now we're going to use that concentration to make this probabilistic so that not every patch will have a diffusing atom. It will depend on the concentration. So the way I'm going to do that is I'm going to make an if statement, and I'm going to get a random float, which is a decimal number, between 0 and 1. And then I'm going to say if that's less than the concentration, then go ahead and do this. Now what this is going to end up doing is each patch with a probability equal to the concentration is going to run the commands inside of the if statement. And the reason that is I will let you think about, but you can go and imagine if you're picking a random number somewhere between 0 and 1, how likely you are to get a random number that's less than the concentration. So now when I click setup, looks pretty good, looks like it's about 30%. If we make this 0, we should get 0. Yep. If we make it 100, we should get 100. So it looks like this is working. And so now we can set the concentration and have our diffusing atoms moving around. And this is a very simple model of interstitial diffusion. And the last thing I will do is create a plot so that we can see our concentration profile. This is something you've actually already seen, because all we need to do here to get a concentration profile is see how many diffusing atoms are in each column. So I'm just going to histogram the x-coordinates of my diffusing atoms. And I'm going to set this concentration profile up on top of the world so that we can get the x-axis of this graph to line up with the x-axis of the world. So if I set this x-min and x-max to the size of the world, set things up, and so now this is showing the number of diffusing atoms in each column. So this at patch -1, which is this column, looks like there's a peak, and it does look like there's more in that column compared to here. There's a little bit of a trough, and it does look like there's fewer in that column. And as things diffuse around, this will fluctuate because we have a relatively small number of atoms. And so the number in each column is fluctuating up and down. Okay, that's it for now. You'll be seeing a slightly modified version of this in class and exploring it. Good luck.